The objective of this video is to introduce the topology and operation of three-phase voltage source inverters. If somebody is talking to you about an inverter and they don't specify what kind of inverter it is probably a three-phase voltage source inverter. Voltage source inverters are the most common type of inverter in power electronics when you're talking about a few kilowatts and higher. And they are very prolific throughout the motor drives industry, throughout wind energy generation, uninterruptible power supplies, all of the applications that we outlined last time when we talked about single-phase inverters. Three-phase inverters also factor in and are in fact more prevalent. So we're going to introduce this by building up from the half-bridge converter topology that we discussed in our previous video. And I've sketched it on this page, but I've sketched it in a little bit of an unconventional manner. You'll see that I've elongated the circuit because we're going to be adding additional single-pole double-throw converters or additional half-bridges. And I've also drawn our pole current as having an impedance. And we're assuming that that impedance is inductive, so it's actually a current source. And then you see that I've sketched it traveling along the bottom here and coming back up. And this is just anticipating what we're going to add to this converter to make it the full three-phase converter. So as it's sketched right now, this is just the half-bridge converter that we talked about previously. So if we review some of the key results that we had from our analysis of this, we can write an expression for our average pole voltage as being D11 times our throw voltage, which in this case is VDC. And we're again assuming that D12 is simply equal to 1 minus D11. And so if we do this, we can get an expression for our V1 voltage. That's the voltage across our impedance or our load. And since this is an inverter, we desire for this to be an AC signal. And if we solve this for our duty ratio, we get the following. Where we had previously noted that this quantity right here is our modulation index, M. And so we can finally write V1 in terms of the modulation index. Where you'll recall that M was allowed to vary between 0 and 0.5. If M is larger than 0.5, we end up with a duty ratio that's greater than 1, which we know cannot happen because we cannot have a pole connected to a throw more than 100% of the time. So we can write this voltage expression, we can put it into phasor notation, and this is a throwback to our early days in this class when we reviewed different ways to express power electronic quantities. And so we'll do this as an RMS phasor, which has a magnitude of V out hat over square root of 2, because this is a sinusoidal quantity, so we can convert between the RMS value and its peak value by just dividing by square root of 2. And then we can note that we can talk about the current I1 that's flowing as just being this voltage divided by the impedance. So all we've done here is solve this circuit where we've noted that we have a voltage across an impedance which will give us a current. We take our voltage divided by our impedance and we get our current. And we've done this in the phasor domain. And then we've expressed our current as having a peak value, which we converted to an RMS quantity, and then some angle phi relative to our voltage. And this is inductive, so presumably phi is negative, so the current will lag the voltage. So what we do to build this up into a three-phase inverter is that we add subsequent half-bridge legs to this converter. So let's add a second leg. And similarly to how we wrote out voltage and current expressions for the first leg, we can do the same thing for the second half bridge leg that we have just added. And in this case, we desire our output voltage, because we're talking about a three-phase system, to be delayed from the first phase by 120 degrees. So if you recall, a three-phase system consists of phases A, B, and C, where phase A has an angle of 0 degrees, phase B is delayed from phase A by 120 degrees, and phase C is delayed by phase B by 120 degrees. And so next we'll add a third leg to this converter, a third half bridge. And we can write out the same voltage and current expressions again. So we now have a complete three-phase inverter. We're able to, by selecting, we're able to realize this output voltage waveform here for phase 1, and for phase 2 we realize the same voltage waveform but phase shifted by 120 degrees, and for phase C it's again the same waveform but shifted by another 120 degrees. And we realize this by selecting our modulation index to be this V out hat divided by VDC, and then using a duty ratio for each phase leg that is delayed by 120 degrees. So here we got our expression for a duty ratio for the first phase leg and the resulting output voltage. Well, we can continue on with this and derive a duty ratio for the second phase leg and a duty ratio for the third phase leg, each of which is phase shifted by 120 degrees. And we can sketch the phasor representation of this circuit as follows. Where V2 is again phase shifted by negative 120 degrees from V1, and V3 is yet again another 120 degrees. And then we can plot on here, or we can draw on here, our currents, which I'll do in green. And since this is an inductive load, because we have these, we require it to be inductive in fact, so that our currents have stiffness, that means that our currents are going to lag our voltages by some angle phi. And we can then draw the transient representation of this. We can draw the actual phase currents and voltages on a plot down below. You'll have to excuse my poor skills at drawing sinusoids. So we get our voltages drawn on here. We've got V1, V2, and V3. And again, each of these voltages are shifted in time corresponding to 120 degrees. So they're shifted by 120 degrees from each other. Phase V2 is delayed by 120 degrees from phase 1. And we can then sketch our currents as well. Okay, so we now have the transient drawing and the phasor diagram of our voltages and currents. So if we go back up to the circuit up here, I want to point out that I1 adds with I2 and I3 to complete the the current path of I1, I2, and I3 add as going to our passive voltage divider network. And so I want you to think about what the value of the current is going into this passive voltage divider. So take a second and answer the question, what is IN equal to I1 plus I2 plus I3? And you can answer this by looking at the sinusoidal quantities below. Since each of the phase currents has the same magnitude but is just delayed by 120 degrees, we can easily see that the phase currents have to sum to 0. So this equals 0, which means that we actually have no current that takes this path here to this dot that I've labeled. And this dot is actually the neutral point of our system. The neutral point because it is the point that all of our output poles are biased against. We talked about having a common mode voltage in each of our poles. For the half bridge converter, we talked about the common mode voltage being 1/2 of our DC bus value. And the same is clearly true here because these capacitors are holding us at half of that bus voltage. But we're observing that we don't actually need any current to maintain that. So the current on that trace that I've labeled IN is equal to 0, which means that it can have infinitesimally thin copper. It can have 0 copper and you will still maintain the voltage. Everything will still work. So it actually means that you can remove that trace. So since IN equals 0, the capacitive voltage divider network is not needed. So let's resketch this converter down below without that voltage divider network. And so this is the standard voltage source inverter. We've removed the deliberate drawing of impedances because we might connect it to any arbitrary load. But the point is that the load actually does have to be current stiff, so it needs to be inductive in nature. A typical load will be an electric motor, and electric motors have coils wound around stator teeth, which look a lot like inductors and transformers, so an electric motor is a very inductive load. And if we focus in on the single pole double throw switches that we've drawn here, so if we draw an exploded view of how this is actually implemented, then a voltage source inverter is going to be implemented with the semiconductor realization for a positive throw voltage but a bidirectional throw current, or a bidirectional pole current, just like the bridge converter was implemented. And so these switches are pulse width modulated in order to realize the 3-phase output voltage that we desire from our inverter. And you can buy these modules. You can buy modules that implement this switch configuration, that is 2 diodes and 2 MOSFETs. That would be called a half bridge module. You can also buy what's called a 6-pack, which implements all 3 of these legs. So it will have 6 MOSFETs, or 6 IGBTs, and 6 diodes. And so if you buy a 6-pack, you will have terminal connections at just the power points of the converter. So you provide your own DC link, so you have a terminal connection on the positive and negative portion of your throw voltage, and then you have terminal connections right on the output of each of your phase terminals. So you have 5 connections, and then in addition to that, you'll have connections for the gates of each of the switches in there, whether they're IGBTs or MOSFETs. And these 6-pack modules can be rated to very large quantities. From DigiKey, you can easily find parts that are on the order of 1200 volts and a couple hundred amps, and via more direct ordering, you can get this into the hundreds of kilowatts, if not megawatt range. And so this is how large power electronics are implemented. So before we wrap up, I want to make one more comment on this neutral wire connection. So again, the neutral wire was what we highlighted in green here. It's the connection that went to our passive our passive voltage balancing network, or a passive voltage divider. And in the connection that we've drawn on this final page, we don't indicate any neutral wire, but there are certainly three-phase inverter topologies that use neutral wire, or rather three-phase inverter applications that use a neutral wire. And you end up needing the neutral wire when these impedances are not balanced. When they're balanced, that means that Z1 equals Z2 equals Z3. But if they're unbalanced and Z1 does not equal Z2 or Z2 does not equal Z3, then you need to carry a current. IN is no longer zero on that neutral point. And so then in those applications where you're operating loads like that, maybe you have 3 different motors connected across each phase, or different light bulbs, or you can imagine different configurations where you have different loads connected between the phase and the neutral point, that you might actually have a neutral current that you have to deal with. But in traditional motor applications or traditional 3-phase load applications, you don't have a neutral connection. In fact, motor manufacturers don't bring out a neutral point, so even if you had it coming out of your inverter, you couldn't physically connect it because it simply does not exist. And the last thing to point out about this is that I've labeled the neutral point as being at this location right here, but the neutral point by definition is actually where these the three-phase load connects in the center. So it's by definition the average value of the output of your 3-phase legs. And what we've observed right now is that if you were to compare the voltage at this point to the voltage at this point, they're equal to the same value, so you don't have any current that would flow if you connected them, which is why we argued that you could disconnect this line. To wrap up, we've introduced the topology and operation of 3-phase voltage source inverters. We've done this by building up from the half-bridge converter into a 3-phase converter. And then we've reviewed how a half-bridge converter operates and used this to extend into the operation of a 3-phase converter that is pulse width modulated. And the strategy that we're using for pulse width modulation, where we have a duty ratio that is 1/2 plus a cosine, is termed sine modulation. For 3-phase inverters, there's another very popular, if not more popular, modulation approach that's referred to as space vector pulse width modulation. And if you're interested in that, you can take some of our advanced power electronics courses, as this will be covered in detail. We then talked about what our voltages and currents look like in the transient domain, as well as the phasor analysis. And we made the conclusion that we don't need a connection between the neutral of our load and the neutral point of our converter. The neutral point of the converter being VDC by 2, and the neutral point of our load being where the 3-phase loads connect together. And so we drew the final topology of what a traditional voltage source inverter looks like. And we finally made remarks about how you can order packages of these as 6 packs. And you can get them from DigiKey or directly from manufacturers. And lastly, I want to comment on the name of voltage source inverter. Another common name for this is voltage stiff inverter. The idea is that you have a stiff voltage source that's connected across your throw that you're pulse width modulating into AC quantities on your output. So that's where the name voltage source comes from, is that you have a voltage source on your throw, or a stiff voltage source.